We have endeavored to put together a presentation here that will not only inform you, but I believe entertain you. And we were trying to figure out how to get this presentation best across. I was a good part of the planning stage and worked at the Telos Alliance to improve some products that we had to make it fit this model. And we did that. And then Steve Adler drove the high-level discussion of how it would happen, and Matt Stedman has driven a lot of the nuts and bolts into how it will occur. The presentation is called SCAsat, Audio Distribution, Best of Satellite and Best of WAN, and you'll see why. The gentlemen have already been introduced, but they are, again, Matt Stedman, who will be coming up third, Steve Adler, who will speak immediately after me in just a moment, and then there's me, Kirk Harnack. And with that, I'm going to turn it over to Steve Adler. Steve?
Well, thank you, Kirk. Well, welcome, everybody, and thank you for coming along. Look, today I'd like to tell you that Southern Cross Stereo is Australia's largest commercial broadcaster. We have 78 analogue and 25 digital radio stations across 40 markets that covers the breadth of Australia. All our stations combine live and local programming as well as network content, and that certainly does create some challenges for audio distribution. The existing system that we have is very, very old and is really due for change. We wanted the new system that we have now in place to be the world's best and really include an N+1 design just for reliability and redundancy. So we unfortunately couldn't find an off-the-shelf solution. We came to the NAB about 3 years ago really looking for something that we could just buy and plug in, but unfortunately there really wasn't anything that fitted our unique requirements. So we created a request for proposal, an RFP, and put it out to the market, after which we selected a handful of vendors to work together, and their job was to integrate a bespoke or tailor-made solution. I guess the really cool bit, in a world's first, each of our receive sites receive live audio from 2 separate network audio paths. And I must just pause for a moment in Mr. Kim's presentation just prior. It's exactly what we did. We came up with a system that uses 2 diverse technologies that move IP from one place to another. So I really had to smile that he was doing a lot of research on that, and we picked up on that as a really robust way to go, as Matt will certainly explain shortly. So one of those paths, we just use traditional satellite. Satellite, we found, is a very robust delivery mechanism. It's one point to many. It really suits a continent like Australia because it's just so vast. But it does have its foibles, which we'll talk about. We also installed a brand new wide area network from Australia's biggest telco. They're called Telstra, very similar to AT&T here, I guess, in the United States. And they were the only telco that could pull it off for us. So we bought a beautiful meshed IP network from them to form half the basis for this system that we have. I guess having the 2 increases reliability. So for example, a satellite outage will not cause a loss of any on-air audio, as the wide area network will still deliver the signals and vice versa. So in another world's first, the system is driven using a simple calendar-based scheduler. So all the hardware is transparent to the user, and we really wanted to make it easy for the content people or the programming people to use this system, so they didn't have to worry about the complexity behind it. They would just see a very simple user interface. So, the problem. Each of our 78 stations broadcast a mix of local and network content, and that just changes through day part. The content can come from any of our 10 head-end stations at any time of the day, and these head-end stations are dotted all around Australia, and as I just said previously, the programming can simultaneously just change on an hour apart. A standard broadcast day is so complex that no one person in our organisation knew exactly what was being fed or from where. A lot of our programs are huge brands in their own right and really do command large audiences. So generating a large amount of content certainly has an effect on SCA's revenue. Getting all of these programs delivered reliably across the country was difficult. Due to organic growth within Southern Cross Austereo through mergers and acquisitions, we were using 6 different distribution systems that didn't talk to one another. And I guess this all came about, and I guess we've all been through this, when there are mergers and acquisitions. Engineers probably get about 10 minutes. Well, oh guys, you've got this, just make it work. And we tend to do that within minutes, and then usually the systems tend to stay that way forever, and that's pretty much what we had. A lot of them had single points of failure that could cause significant outages. And I guess lastly, and probably the most importantly, all the existing equipment at the time was at end of life. The newest component was installed back in 2001, and ironically, I worked for the company back then, had a little 14-year hiatus, and that equipment was still there, so it's amazing what can come back and bite you. So here's a snapshot of the inefficiency of the old system. We create network program at 2Day FM in Sydney. It gets sent via a Harris Intraplex audio codec to Melbourne at 256 kilobits per second MP2 and decoded back to audio. This is then repackaged, re-encoded and sent up to CFM on the Gold Coast, which by the way is a fantastic tourist destination if you're ever thinking of visiting Australia. This is sent as a 256 kilobit per second MPEG-3 stream, so you can already see we've got concatenation but completely 2 different compression techniques. It's decoded again in the Gold Coast where it's repackaged and then re-encoded onto a satellite uplink running 256 kilobits MPEG-2, and I'm sure you're all starting to groan in your minds of what this is starting to sound like. So this is the 3rd encode process so far. The satellite signal which covers all of Australia, sorry, I beg your pardon. The satellite signal covers all of Australia and New Zealand, and one of our stations, Hot FM in Bunbury in Western Australia, then receives the stream and decodes it back to audio. Hot FM in Bunbury then feeds its own mini network in southwest Western Australia, but this time the audio is re-encoded at 128 kilobits MPEG-2. So by the time it is received at all the nodes in regional Western Australia, there's really been about 5 separate encode-decode cycles. And to be absolutely honest with you, on FM it sounded like high-quality AM. It really, really was poor, and that was purely because of this concatenated delivery mechanism. So the cascading of systems caused some really bad audio, which I just said. Also, if any of these individual systems suffered a fault, or even something quite normal like rain fade on the satellite uplink or the downlink, whole regions could simply go off the air. Even worse, if these outages coincided with a pulse that would start a commercial break, our stations would then be out of sync, requiring human intervention on the audio playout system to get them back into sync. And I've got to tell you, the listener experience was absolutely terrible when that happened, because it took time to go around and fix all the sync problems. So obviously if the commercials didn't air, this caused loss of revenue and a really bad result for our listeners and our business. So how do we fix this? Well, I guess like some of the best projects, we started off with a blank piece of paper and captured our current and future needs. We then searched around the world for the best technology solutions to integrate what we think is the most robust distribution network operating today. Despite there being some amazing companies producing great hardware, we couldn't find a single solution that met our needs, as I talked about earlier. So, like all good engineers do, we started thinking about how we could integrate some of the great products we saw to create what we needed. So we ended up partnering with Telos for audio codecs, Axia Audio for the local audio over IP codecs, AVC for the system supply and creation of the unique management software, which is absolutely unique. And actually we have Igor Zukina sitting in the audience here, and he really was the brains behind that, and it is superb. All good systems that are IP-based, of course, need excellent routers and switches, so we exclusively use Cisco. And Novra, a Canadian-based company for a IP satellite receiver. We also partner with a company called AVW for their satellite experience, Newtek and Terasat for their satellite uplinking equipment, which I might just digress and say one of the other things that we did to keep reliability in the system was to have diverse satellite uplinks. So we have actually one in Sydney and one in Melbourne, and they detect rain fade on the uplink and automatically switch, which is just elegance. It's absolutely superb and works really well. So we tied it all together and we created the thing called SCAsat. So now I'm going to hand over to Mr. Matt Stedman here, who really was the architect and systems administrator and pulled this whole thing together. So over to you, Matt.
Hello. Thanks, Steve, and thanks, Kirk, and thanks, of course, James. So I'll run you through, I guess, some of the more nuts and bolts side of this system that we built. Hopefully it'll give you some understanding of the benefits of it and the reasons that we went down this path, and we think it's a really good system. We're happy to share it as much with you as we can. So, as Steve mentioned earlier, the heart of this SCAsat system is the Telos iPort audio codec. Obviously, an audio distribution network is reliant on getting audio streams across the country. That's what it does. So we looked at a lot of the competing products and went with the Telos iPort. The iPort handles all the encoding, decoding and transfer of audio around the SCAsat network, which is obviously the key function of its role. Each of those Telos iPorts can contain 16 codecs that send and receive simultaneous audio streams across different diverse network paths, and we'll come back to that because it's a really key point. And it really is the point that we think makes SCAsat different to any of the other audio distribution networks on air at the moment. Are you clicking? You're clicking, there we go. Kirk's on clicking duty. SCAsat delivers all of its audio to each receive sites twice. So all of our radio stations receive the same audio via two different methods. We chose satellite as the main distribution path because, as Steve said, satellite works. It's one-to-many. It's still, we think, the best place or the best way to get audio from one place to many places on a continent the size of Australia. But satellites do go wrong. Rain fade, technical failure, equipment maintenance, all of these sorts of things can interrupt the ability for satellite to supply signal to a receive site. So what we did is we send a second copy of the same audio across the whole country to each of the receive sites via the wide area network, or I guess computer network. The deployment of these simultaneous streams, it practically guarantees the receive sites will receive audio. So a failure of either one of those two paths won't actually cause any effect at the receive site, other than, of course, generate an alarm for us engineers to deal with. But of course, all this technology would be completely meaningless if you can't easily manage it. So we partnered with AVC to develop a customised scheduling system that controls what sites are sending to what channels at what times. There's actually 15 audio channels on the SCAsat system, and determining which site is sending audio to and from those channels is the role of this management system. It's quite a complex equation, as you could imagine, given that we have different shows from different sites on different hours of the day. But despite all that complexity under the hood, the front end is really, really simple for the content users to drive. Effectively, we said to them, if you can schedule a meeting in Microsoft Outlook and click and drag a little appointment into the calendar, you can effectively drive your radio network, which is great. So us as engineers, we only get involved in program distribution and exchange when there's a technical fault, and the rest of it is self-serve. So we're going to have a look at the iPort in a little bit more detail because it really is what makes SCAsat work. And there's a lot of really good codecs on the market at the moment, and most of them are exhibiting downstairs. But we chose the iPort for three key reasons. The first one, as we mentioned earlier, is density. So you've got a single 2RU box, and that contains 16 bidirectional audio codecs, which is quite a good value proposition. Each of those codecs can also accept GPIO signals. And also, this is new, as well as GPIO or pulses or what you might call them, we can also now, via any of those encoders, encode any UDP data packets generically into that audio stream as well. So you're not reliant necessarily on certain pulses or protocols. You can send generic user datagram protocol packets through any of those 16 codecs. More on that later. The second one is the multiple delivery paths. with most IP codecs, you just enter the IP address of the codec that you want to communicate information with, whereas with iPorts, we enter two, one for each network segment. They're completely discrete and simultaneous. So to give you an example of that, we subscribe to one multicast stream to get audio over the satellite, one IP address, and a second to receive audio via the wide area network, and it receives both simultaneously. So the really critical point of this is it doesn't switch. It just accepts packets on both of those network paths simultaneously, and as long as it sees a valid packet, it will actually transmit audio and all the other good stuff comes out the other end. So the third one is time zone delay, and again this is a really key requirement for us, which we'll talk a little bit more about later, but effectively the Telos iPort also handles our time zone delaying requirements as well. Now the advantage of that is we only need to uplink each audio stream once, so our satellite bandwidth and WAN bandwidth usage is very, very efficient. We've talked a little bit about the technology. Where does all of this audio come from? Australia is a big continent. I think it's probably a very similar size to the continental United States of America. Right now we generate our audio from 10 radio stations that are dotted around that country. This is simply a legacy constraint. There's no technical reason why we couldn't introduce more. It's just where the content comes from right now. So we can add more contribution sites at any particular time. And as Steve said, to maintain redundancy, we actually have an uplink site both in Melbourne and in Sydney, which is kind of not really shown, but automatic failover of the uplink sites as well. But only one uplink radiates at a time. It's literally an AB situation. All that uplink does is take all those standard audio IP encoded streams and radiate a single DVB-S2 carrier up to the satellite, and that's got the entire channel suite, all 15 channels on that carrier. Whichever site is actually radiating at any time, be it Melbourne or Sydney, they also provide the IGMP subscription for the WAN-based streams, and we'll talk a little bit about the way we get around that later on. But critically, both of those streams, the satellite stream and the wide area network stream, are received at all of our receive sites. At the moment we have, as we said, about sort of 40 to 45, but there's absolutely no reason why if we have further mergers, acquisitions or further affiliates, we just put a satellite dish on the roof and away you go. So a little bit more detail. Here's what we installed across each receive site. The main point of this slide is not so much to run you through it in a huge amount of technical detail, but also to note the redundancy. So at each receive site, we've effectively got two of everything. You'll note, so if the iPort were to fail, then we have a second one, etc., etc., etc. And the way that actually looks when we look at the packet flow, Kirk's a bit excited on the clicker. The way that actually looks when we look at the packet flow is, we have to wait for the animation now, don't we? We have the satellite stream coming in that feeds directly one side of the iPort and the WAN-based stream that feeds the other side of the iPort. But the really critical thing is there's no single point of failure on any of those receive sites. Here we go. So the red path there is the received satellite signal. So single dish at each site, just because redundant satellite dishes seems a little bit over the top. However, two receivers providing multicast streams into the two iPorts, and then a single wide area network connection, but providing the same multicast packets to both iPorts as well. So really robust. There's not much there that you can kill that will actually result in a loss of audio, which is great news. We just touched on this earlier, that the differences between the satellite and the wide area network paths are the fact that on the satellite, of course, we have a chunk of bandwidth. We have about 2 megabits per second, and that contains all 15 channels all the time, just via standard multicast packets. The difficulty, though, with replicating that on a wide area network would be the bandwidth requirements at each site. So 2 megabits per second actually doesn't sound like a huge amount, but at some of our regional sites in Australia, at some very small towns and cities, to get a guaranteed 2 megabits per second is, to be honest, quite expensive. So what we wanted to do is only have the signals that are required at that particular site transferred through the WAN. And we do this via IGMP. So we have all 16 streams available on the satellite at all sites at all times. However, the iPort is clever enough to only request the multicast packets that it actually needs, that it's actually set to receive, and that's what comes through the WAN. So that's how we minimise the bandwidth on the wide area network, and it works really kind of well. A key problem, as Steve mentioned, with the old system was the number of encode and decode cycles. It was just a mess. We won't go to that again. We're trying to put it out of our minds. The really good thing is SCAsat only encodes once. So as the audio enters the network, the announcers are talking into the microphone at the Gold Coast, for example, and it gets encoded at the Gold Coast. The only time it's ever touched after that is when it's decoded at the final receive site. So we get rid of all that concatenation. All of the other switching and routing is done in the IP domain. We also, as well as audio, made a pact when we designed the system that we wanted to get away from a lot of the old traditional relay closures and GPIOs and RS-232 signalling. We thought if we're going to build this great system, we should make everything via internet protocol only, so everything should just come through the single cable. This is again where some of the technology we selected helped. So the Telos iPorts natively talk the Axia Livewire GPIO protocol, which we use internally for commercial start or stop-set start pulses, jingles, liners, and those sorts of things. So we don't actually require any pulsing or 232 to get that working. And the other cool thing is we mentioned earlier is if the Livewire GPIO protocol is unsuitable, we can actually now send generic UDP information through these audio streams. Everything is actually bundled up together into the same audio stream, so it's all completely time aligned. You effectively send the pulsing information into the encoder, and then it comes out at the other end, all beautifully time aligned, just as you sent it in. The other feature that we mentioned is Australia has a lot of time zones, again similar to the US, and they all take various different shows that are produced at different times. One way that this is made really easy is the fact that the Telos iPort can actually delay each of those encoded streams on a stream-by-stream level for a completely configurable amount of time. So some of our sites run in a single fixed 1 hour delay, so we set the iPorts to play back the received stream at 60 minutes after they receive it. And the good thing about that is you still get all of your pulses, all of your GPIO information, all at the same time, because effectively it's the same audio stream. Everything comes out effectively just like it went in. We'll go a couple of quick slides on scheduling, because we're sort of talking a lot about the technology, but the other really cool part of this is the way that it's scheduled and driven. So we have 78 radio stations. We've currently SCAsat set up with 15 channels, but prior to SCAsat, the process of setting up different programs and audio exchange was all just verbal fundamentally. So the content guys would want to put a show on at a certain time. They would have to ring engineers. The engineers would have to engineer a way to make that work across these 6 distribution systems, and it was just a real mess. What we have now with SCAsat is this. I think it was supposed to. Oh, there we go. There it is. We have this one single scheduler display which controls the entire system. So there's no middleware in this. The scheduling software actually directly talks to the encoding and decoding equipment. As you can kind of see there, it's basically looks like a calendar view. AVC created this for us and integrated the system completely. So our key component was to make it very easy to drive, make it look like an Outlook calendar, and effectively just look at conflict resolution, those sorts of things. But again, this talks directly to the iPorts. There's no middleware, and I think you can sort of agree the content staff would find that pretty easy. So if you can click and drag around Microsoft Outlook, then we think you can effectively drive our radio network, which is a really exciting thing. That's all I had. I was going to transfer back to Steve just for a quick wrap-up of the business benefits and summary. Thank you, Steve.
Cheers. So how has SCAsat improved Southern Cross Austereo's business? Well, as Australia's leading commercial radio broadcaster, reliable delivery of on-air to Southern Cross Austereo's radio network is critical to our business performance. As mentioned earlier, the old system was no longer viable, and this was a direct threat to our ability to deliver results for clients and listeners. Through SCAsat, we benefited Southern Cross Austereo via redundancy and reliability, so no more technical off-airs, better audio quality, which we've touched on, newer equipment, so lowers the risk of failure, and more channels, which means we can give content far more flexibility. Most importantly, our operational costs halved, which management certainly likes. It now takes less time for operational staff to carry out their duties, thus giving them more time for higher value tasks. We have future opportunities for even greater flexibility and efficiency. So in summary, we've identified some very serious flaws and risks to the old system. We partner with multiple vendors to create a live distribution system called SCAsat. World's first in dual-path technology. Turn off the satellite, no problem. Turn off the WAN, no problem, as long as each other's on. Turn off both and you've got a problem. So this gives us more channels, more flexibility, better audio and greater reliability. Our connections between sites are driven at a user level, freeing up operational engineering time, and it's the world's first object-oriented scheduler directly controlling the equipment, as Matt said. If you can drive Microsoft Outlook, you can certainly drive our network. And we've halved the operational costs of all the audio distribution as well as delivering all these improvements. We think it's great. We hope you do too. And as always, we're happy to take any questions after this presentation.
Thank you very much, Matt Stedman and Steve Adler from Southern Cross Stereo. Do we have time for a question or two, if there are any?
Gentlemen, Marty Sachs from Telos. I have a quick question. How much time have you spent on the WAN versus satellite uptime?
This gives up, actually, they have an excellent story to tell about this that has to do with emergency preparedness and emergency operations. Go ahead, Steve.
Yep, certainly. So, look, the majority of the time is on the satellite because it just is the one-to-many solution. But of course, the WAN is going really all the time as well. But look, anecdotally, what I can tell you, recently in North Queensland, we had a weather event. Was Cyclone Marcia went through, and actually the eye of that cyclone, which was a Category 5, so the worst, went straight through a city of Rockhampton, and we'd already cut over to SCAsat there. So what had happened is the winds got up to about 300 kilometres per hour, and actually blew the satellite dish off course. So just like a sail, it carried it off. And the WAN, being fibre-based, terrestrially based, actually kept going. It came to a point where we had to evacuate that building, and part of our licence charter is we have to provide emergency communications and to our listening public to advise them what to do. So we had to evacuate the station. So we then continued programming on from one of our other sites up further north in Cairns and actually kept the whole system on the air. So it might just give you some idea of the availability of the two.
So from Cairn, they programmed the emergency information for the audience in Rockhampton, via the WAN because the satellite was out.
Correct.
And just to be really clear, you said this earlier, but the audio is, the packetized audio is replaced on a packet-by-packet basis if there's a problem. So if there's one packet missing from the satellite, well, that packet is already waiting in the buffer from the WAN. So you can turn one off and the other off back. And in fact, we tested this, didn't we?
We did.
Just turning them off back and forth. Now, we turn them both off, the audio does stop.
It stops.
Any further questions? If not, thank you very much for your attention.
Gentlemen,
James?
thank you very much.
Thank you, Jim.